Module 15, Lecture B, Probability Calibration. By the end of this lecture, you will be able to evaluate probabilistic predictions using calibration curves and proper scoring metrics, calibrate classifiers with sigmoid and isotonic methods using cross-validation, and apply isotonic regression for monotonic calibration-style relationships. Calibration metrics. Probabilistic predictions. Probabilistic predictions express uncertainty by giving likelihoods rather than definite answers. This helps with calibration because decisions often depend on how confident a model is, not just on which outcome is most likely. For example, a 51% risk and a 95% risk may require very different actions, even if both point to the same outcome. Overall, probabilities support more nuanced decisions by making risks and benefits clearer. A probabilistic prediction is well calibrated when its stated chances match what happens across many cases. If a model often predicts a 70% chance, about 70% of those events should occur over time. This does not guarantee any single outcome, because probability describes uncertainty across groups. Calibration measures how trustworthy the predicted probabilities are, not just whether the model picks the correct class. Model performance should be judged by both discrimination and calibration. Discrimination shows how well a model separates higher risk from lower risk cases, while calibration shows whether its predicted probabilities are trustworthy. A model can rank cases well, but give probabilities that are too high or too low. So both measures are needed for useful predictions and better decisions. Python code. Probabilistic predictions. This script evaluates whether predicted probabilities are reliable by comparing predicted risk with the actual frequency of events. It highlights the difference between perfectly calibrated, well-calibrated, and overconfident predictions. We import tools for numerical work, visualization, and model evaluation. NumPy handles arrays and calculations, while Matplotlib creates plots. Scikit-Learn provides version tracking for reproducibility, a calibration curve tool to compare predicted probabilities with real outcomes, and scoring metrics such as Brier score loss and log loss to evaluate probabilistic predictions. The example uses a fixed random seed, so the results are reproducible. It creates 2,000 true event probabilities, spread uniformly between 0.02 and 0.98. Then it simulates binary outcomes from those probabilities, indicating whether each event occurred. Two probability prediction models are compared. The calibrated model reports the true probabilities directly, so its predictions reflect the underlying data honestly. The overconfident model squares the true probabilities, making predictions seem more certain than they really are. Comparing them shows how confidence levels affect the accuracy and reliability of probabilistic predictions. The code compares calibrated and overconfident probability predictions using the Brier score loss. This metric measures the average squared difference between predicted probabilities and actual outcomes. So, lower scores indicate more accurate probability estimates. We compare log loss for calibrated and overconfident probability predictions using Scikit-Learn's log loss function. Calibrated predictions are checked against the actual outcomes to see how well their probabilities match reality, while overconfident predictions show how exaggerated certainty is penalized. This makes log loss useful for judging the reliability of predicted probabilities. This code uses Scikit-Learn's calibration curve function to check whether predicted probabilities match real outcomes. It groups the predictions into 10 bins and compares the average predicted probability in each bin with the actual fraction of positive cases. The result helps show how well the model's probability estimates reflect observed frequencies. We use Scikit-Learn's calibration curve function to check whether predicted probabilities are overconfident. It groups predictions into 10 equal-sized probability bins, then compares the average predicted probability in each bin with the actual fraction of positive outcomes. This shows how closely the model's probabilities match real observed frequencies. The script reports the Scikit-Learn version to support compatibility and reproducibility. Then it compares a calibrated model with an overconfident model using two probability metrics. It prints the Brier score, where lower values mean better calibration, and the log loss, which penalizes poor probability estimates more strongly. Together, these results show how well each model's predicted probabilities perform. The plot compares model calibration against a reference line for perfect predictions, where predicted probabilities match observed outcomes. One curve shows the model with honest probabilities, using connected circles, while another shows the overconfident model, using connected squares. The labels distinguish the calibrated model from the overconfident one, and make it clear how each model's predictions align with reality. The plot is set up as a calibration curve for probabilistic predictions. Its axes compare the model's mean predicted probabilities with the observed frequency of positive outcomes. Both axes run from 0 to 1, so the full range of possible probabilities and observed frequencies is shown clearly. The legend function adds labels that identify the lines for perfect calibration, calibrated predictions, and overconfident predictions, making the plot easier to interpret. The Matplotlib show function then displays the plot, so we can visually assess how well the probabilistic predictions are calibrated. This script checks how reliable predicted probabilities are by comparing them with real outcomes. It contrasts a well-calibrated model with an overconfident one, using Brier scores and log loss to measure probability accuracy, where lower values are better. The calibrated model performs better, and its calibration curve stays close to the ideal diagonal, while the overconfident model deviates, showing less trustworthy probability estimates. Calibration curves. A calibration curve shows whether a model's predicted probabilities match what actually happens. For example, when a model predicts a 70% chance, about 70% of those cases should occur if it is well calibrated. This matters because a model can rank risks correctly, but still give misleading probability levels, which can lead to poor decisions. A calibration curve checks whether predicted probabilities match real outcomes by grouping similar predictions and comparing them with observed frequencies. Points close to the perfect calibration line show reliable predictions. If the curve falls below the line, the model is overpredicting. If it rises above, it is underpredicting. This helps reveal confidence problems in important decisions, such as loan approvals or weather warnings. When reading calibration curves, consider the sample size, how predictions are grouped, and where predicted probabilities are concentrated. A rough curve may reflect noisy or sparse data, rather than a bad model, and clustered middle-range predictions may say little about extremes. Use calibration curves with numerical metrics and domain knowledge to judge whether a model's uncertainty is reliable in its real deployment setting. Python code, calibration curves. This script creates a simple calibration curve to compare predicted probabilities with actual observed frequencies. A well-calibrated model should closely follow the diagonal line. We import key Python libraries for building and evaluating a classification model. NumPy supports numerical work, Matplotlib creates visualizations, and Scikit-Learn provides tools to generate a synthetic classification dataset, split it into training and test sets, and fit a logistic regression model. We also include probability evaluation metrics, such as Brier score loss and log loss, along with a calibration curve to check how closely predicted probabilities match actual outcomes. We create a small synthetic dataset for binary classification using Scikit-Learn's make classification function. It includes 1,200 samples with 8 features, 5 of which are informative and 1 redundant. A fixed random state ensures the data can be reproduced, giving us a controlled setup for testing model calibration. The dataset is split into training and testing sets using Scikit-Learn's train-test-split function, with 35% reserved for testing. Stratifying by the target keeps the class balance the same in both sets, and a random state of 42 makes the split reproducible. This lets model calibration be evaluated on unseen data. Before evaluating the model, confirm that the test set includes both classes. This ensures performance is measured across all possible outcomes. If only one class is present, raise an error, because the evaluation would not be valid. We create a logistic regression model for binary classification, giving it enough iterations to converge, and setting a random state so results can be reproduced. We then train the model on the training data so it learns how the features relate to the target. During training, the model adjusts its parameters to reduce the gap between predicted and actual outcomes. We use the logistic regression model to estimate the probability of the positive class on the test data. The model's predict probability method returns probabilities for each class, and we keep the positive class values. These probabilities are important for assessing how well the model estimates positive outcomes and for later calibration analysis. We evaluate the model's predicted probabilities using the Brier score and log loss. The Brier score checks how well the probabilities are calibrated, with lower scores being better, while log loss penalizes confident wrong predictions more strongly. Together, these metrics show how closely the model's probabilities match the actual outcomes. The code uses Scikit-Learn's calibration curve to check whether predicted probabilities match actual outcomes. It compares the true test labels with the model's positive class probabilities, grouping predictions into 8 uniform bins. For each bin, it calculates the actual positive rate and the average predicted probability, which together show how well the model is calibrated. We first report the Scikit-Learn version to support compatibility and reproducibility. Then we review the Brier score and log loss, 2 metrics for judging predicted probabilities. Lower values for both indicate better alignment between the model's probability estimates and the actual outcomes. This plot creates a calibration curve to compare a logistic model's predicted probabilities with the actual observed positive rates. A dashed diagonal line shows perfect calibration, where predictions match outcomes exactly, while the model's points show how closely it follows that ideal. The axes are limited from 0 to 1, labeled for predicted probability and observed frequency, and a legend helps distinguish the reference line from the model curve. This script evaluates how well a logistic regression model estimates probabilities on a synthetic binary classification task. After training the model and predicting positive class probabilities on test data, it measures probability quality using the Brier score and log loss, where lower scores are better. It then plots a calibration curve comparing predicted probabilities with actual positive rates, showing whether the model's probabilities closely match real outcomes. Brier log loss. The Brier score and log loss evaluate probabilistic predictions by checking how well a model expresses uncertainty, not just whether it chooses the right class. This matters because a prediction of 20% risk should be judged differently from 90% risk, even if both lead to the same label. The Brier score measures the squared difference between predicted probabilities and actual outcomes, rewarding confident correct predictions and strongly penalizing confident wrong ones. In this way, it reflects both accuracy and calibration, helping ensure predicted probabilities match real-world frequencies. Log loss, or cross-entropy loss, measures how well a model's predicted probabilities match what actually happens. It strongly penalizes confident wrong predictions and rewards high probabilities assigned to true outcomes. This encourages models to avoid extreme certainty unless it is well supported, making log loss useful in high-stakes areas like finance and healthcare, where reliable probability estimates matter. The Brier score and log loss are both proper ways to evaluate probabilistic predictions, but they emphasize different things. The Brier score is easy to interpret because it behaves like an average squared error, while log loss is often useful in training because it rewards well-calibrated confidence and penalizes confident mistakes. Using both metrics, along with calibration curves, gives a clearer view of whether a model's probabilities are accurate and reliable. Python code, Brier log loss. Simple probability forecasts can be compared using scoring rules. The Brier score measures the squared error in predicted probabilities, while log loss gives especially large penalties to confident predictions that turn out to be wrong. The script imports key tools for numerical work, visualization, and model evaluation. NumPy handles efficient array operations. Matplotlib creates plots for comparing results. And Scikit-Learn provides scoring methods for assessing probability predictions, including Brier score loss and log loss. It also imports Scikit-Learn itself, so the library version can be checked for compatibility. This creates a NumPy array of actual event outcomes, using ones and zeros to show whether each event occurred. The array can then be compared with predicted probabilities from forecasting models to assess prediction accuracy. Three forecasting styles are being compared through their probability predictions. Careful probabilities use moderate values, such as 70% and 30%, while overconfident probabilities use extreme values, such as 99% and 1%. Underconfident probabilities stay close to even odds, such as 55% and 45%. These prediction sets will be checked against actual outcomes to evaluate their accuracy. The probability forecasts are stored in a dictionary, so each forecasting style can be referenced by name. Labels such as careful, overconfident, and underconfident point to their corresponding probability arrays. This makes it easy to retrieve and loop through each forecast set later for analysis. The process checks each forecast set to make sure its probability predictions have the same shape as the actual outcomes. If a mismatch is found, it raises an error identifying the incorrect forecast set. This validation helps ensure the data is consistent before any further calculations are performed. The process evaluates each forecaster by computing two performance metrics for its probability predictions. For every set of forecasts, it calculates the Brier score, which measures squared prediction error, and log loss, which penalizes confident wrong predictions more strongly. Each forecaster's name and scores are stored together, creating a compact summary of prediction performance. The code first reports the Scikit-Learn version to clarify the running environment. It then reminds the user that lower Brier scores and log loss values indicate better performance. Finally, it prints each forecaster's name with its two scores rounded to 3 decimal places, making the results easy to compare. We extract each forecaster's name along with their Brier score and log loss from the score rows. These values are organized into separate lists, so the forecasting styles can be compared visually by performance. To prepare the bar chart, we assign x-axis positions based on the number of forecast names and choose a bar width of 0.35. We then create a Matplotlib figure and axes with a 7 by 4 inch canvas. This sets up the plot for comparing Brier scores and log losses. The chart compares probability forecast quality using two metrics, Brier score and log loss. For each forecast style, the Brier bars are placed slightly to the left and the log loss bars slightly to the right, making the two measures easy to compare side by side. The plot is titled to show that it compares these metrics, and the x-axis is labeled by forecast style. The code finishes the plot by labeling the y-axis to show that lower scores mean better performance, placing forecast-style names along the x-axis, and adding a legend for the Brier score and log loss bars. It then displays the chart so the viewer can compare how the different forecasting styles perform. This script compares careful, overconfident, and underconfident probability forecasts against actual outcomes using Brier score and log loss. The Brier score measures overall probability error, while log loss gives a stronger penalty to confident predictions that are wrong. After checking that the predictions match the outcomes, the script reports both scores for each forecasting style, where lower values mean better performance. A bar chart then helps compare how caution, overconfidence, and underconfidence affect forecast quality. Calibration methods. Cross-validated calibration. Cross-validated calibration improves a classifier's probability estimates without reusing the same data for both training and calibration. This matters because a model may rank cases correctly while still giving probabilities that are too high or too low. By calibrating on predictions made for examples left out of each training fold, the method produces more reliable and less overly optimistic probability estimates. To calibrate a classifier, use out-of-fold predictions from the training data and compare them with the true outcomes to fit a method such as sigmoid or isotonic calibration. Then, retrain the classifier on all available data so it can make stronger future predictions. In credit risk, this helps adjust predicted default probabilities so they better match observed default rates. Cross-validated calibration is useful when there is not enough data to set aside a separate calibration set, because it helps use all labeled examples while still producing less biased probability estimates. It still needs an independent test set for final evaluation, since calibration can be affected by the training data. Its quality depends on factors such as the number of folds, classifier stability, and available class data. The goal is to make predicted probabilities meaningful for decisions, not just useful for ranking cases. Python code. Cross-validated calibration. This example shows how to calibrate predicted probabilities so they better match observed outcomes. Cross-validation helps make the calibration process more reliable, and the results compare probabilities before and after calibration. This setup imports the main tools needed for a classification and probability calibration workflow. NumPy supports numerical work, Matplotlib creates visualizations, and Scikit-Learn provides tools to generate data, train a logistic regression model, calibrate predicted probabilities, and display calibration results. The workflow also includes the Brier score to measure probability accuracy, and a train test split to evaluate the model on unseen data. We create a reproducible synthetic classification dataset with 1,200 samples and 10 features. 5 features are informative, 2 are redundant, the classes are moderately separated, and 8% of labels are randomly flipped to add noise. The train test split function divides the data into training and testing sets, with 35% reserved for testing. Stratification keeps the class balance similar in both sets, supporting fair model evaluation. A fixed random state makes the split reproducible each time the code runs. The code first checks how many unique classes appear in the training labels, using NumPy's unique function. Because the lesson focuses on binary classification, the dataset must contain exactly 2 classes. If it does not, the code raises an error to stop training and signal that the data setup is incorrect. We train a logistic regression model for classification, using enough iterations to help it converge and a fixed random state for reproducible results. After fitting it on the training data, we apply it to the test data to estimate class probabilities. We then focus on the positive class probabilities, which show how confident the model is for each test example. We use Scikit-Learn's calibrated classifier with sigmoid calibration to adjust the probability estimates from a logistic regression model. Five-fold cross-validation trains the calibration on out-of-fold predictions, helping reduce overfitting. After fitting on the training data, the model predicts calibrated positive class probabilities on the test set, which can then be compared with the original uncalibrated probabilities. Isotonic calibration can be applied with Scikit-Learn's calibrated classifier tool to improve probability estimates from a logistic regression model. The model is trained with five-fold cross-validation, using isotonic calibration as a flexible alternative to sigmoid calibration. After fitting on the training data, it predicts calibrated probabilities for the test set, especially the probability of the positive class. We compare the uncalibrated, sigmoid calibrated, and isotonic calibrated models using the Brier score, where lower values mean more accurate predicted probabilities. The calibrated models use cross-validation to adjust probabilities, with isotonic calibration offering more flexibility. These scores show how closely each model's probability estimates match the actual outcomes. The output first reports the Scikit-Learn version to support reproducibility, then compares Brier scores for three models: uncalibrated, sigmoid calibrated, and isotonic calibrated. Since lower Brier scores mean better probability calibration, these results show how well each calibration method improves the model's probability estimates. We create a plot to compare calibration curves for three sets of predicted probabilities: the original uncalibrated model, sigmoid calibration, and isotonic calibration. Each curve uses the true test labels and predicted probabilities grouped into 8 bins. This comparison shows how closely each method's predicted probabilities match the observed outcomes. This script shows how to improve logistic regression probability estimates using cross-validated calibration. It creates a balanced synthetic classification dataset, trains a logistic regression model, and compares its original predicted probabilities with sigmoid and isotonic calibrated versions. Brier scores are used to measure calibration quality, where lower scores mean better probability estimates. A calibration plot then compares predicted probabilities with observed positive rates, making it easier to see which method best matches the actual outcomes. Sigmoid calibration. Sigmoid calibration turns a classifier's raw scores into probabilities that better match real outcomes. It is useful when scores rank cases well, but are too extreme or too conservative as probabilities. The method applies an S-shaped adjustment that keeps the original ordering, while making the predicted probabilities more reliable for decision-making. Sigmoid calibration improves the classifier's probability estimates by learning a simple adjustment from held-out predictions and their true outcomes. Using fresh or cross-validated data helps avoid overfitting while mapping raw model scores to better calibrated probabilities. After calibration, outputs are easier to interpret as real probabilities, such as risk scores that better match actual complication rates. Sigmoid calibration is useful when calibration data is limited or when a smooth probability adjustment is needed. Its S-shaped curve can reduce overfitting to noise, making it a reliable and efficient baseline when confidence scores are consistently distorted. However, because it uses a single simple curve, it may not capture more complex or irregular miscalibration patterns. Cross-validation can help improve its probability estimates while keeping overfitting risk low. This script shows how sigmoid calibration can make a decision tree's probability estimates more reliable. After training a shallow decision tree on a balanced synthetic dataset, it compares the model's raw probabilities with probabilities adjusted through cross-validated sigmoid calibration. The Brier score is used to measure accuracy, and calibration usually lowers this score. A calibration plot then shows the calibrated predictions aligning more closely with the ideal diagonal. Isotonic calibration. Isotonic calibration converts a classifier's raw scores into more accurate probabilities using validation data. Unlike sigmoid calibration, it does not assume a specific S-shaped pattern. It only requires that higher scores should not lead to lower predicted probabilities. This helps when raw confidence scores do not match real outcome rates, such as in medical screening, while preserving the original ranking of scores. Isotonic calibration is useful when model probabilities are miscalibrated in ways a simple sigmoid curve cannot capture. It uses a non-decreasing stepwise mapping to correct uneven errors across score ranges, such as underestimating rare, high-risk, or extreme cases. However, it needs enough calibration data because small datasets can make it fit noise and create unrealistic jumps in probability. It works best with a large validation sample and a monotonic relationship between scores and true probabilities. Isotonic calibration needs cross-validation, so the calibration model learns from predictions made on data the classifier did not train on. This avoids overly optimistic predictions and produces a more reliable mapping from scores to probabilities. The result is more trustworthy probability estimates for new cases, which is especially important in areas like credit risk and hospital triage. This script shows how isotonic calibration can improve the probability estimates from a decision tree classifier. It trains the model on a balanced synthetic binary dataset, then compares its raw probabilities with probabilities adjusted by isotonic regression. Brier scores are used to measure accuracy, where lower values mean better probability predictions, and calibration usually lowers the score. Calibration curves then show that the calibrated model's predicted probabilities more closely match the observed outcomes. Advanced calibration. Frozen estimator. A frozen estimator keeps the original model parameters unchanged and adds a calibration layer to make its scores better match real probabilities. Isotonic regression does this with a monotonic mapping, so higher scored cases remain higher after calibration. This improves probability accuracy while preserving the model's original ranking and decision structure. A frozen estimator is useful when the original model is expensive, regulated, or owned by another team, so retraining is difficult. Instead of changing the base model, you can add a calibration layer that uses recent data to adjust its probability outputs. This can improve alignment with real outcomes in areas like credit scoring or weather forecasting. Isotonic regression is one way to correct overly confident probabilities while leaving the model's core logic unchanged. When calibrating a frozen estimator, use data that was not used to train the model. Otherwise, the calibration can overfit and make predictions look too optimistic. A separate calibration set or cross-validation helps produce reliable out-of-sample predictions. Isotonic regression can correct uneven calibration patterns, such as underconfidence at low scores and overconfidence at high scores, but it needs enough data to stay stable. In short, the base model ranks cases, and calibration turns those rankings into more accurate probabilities. This script shows how to improve a logistic regression model's probability estimates using isotonic calibration. It creates synthetic data, separates it into training, calibration, and test sets to prevent data leakage, trains the model, and then calibrates its predicted probabilities without changing the trained model when possible. The results compare raw and calibrated predictions using Brier scores and calibration curves, where lower scores and closer alignment with perfect calibration indicate better probability estimates. Multiclass probability calibration. Multiclass probability calibration means a model's predicted probabilities should be reliable across several possible outcomes, not just a yes or no decision. For example, a medical or weather model should express uncertainty accurately for each option, not only for the most likely one. If it predicts rain with a 40% chance, rain should occur in about 40% of similar cases, while the remaining probability is reasonably assigned to other conditions. To calibrate multiclass probabilities, handle each class as a one versus rest problem and adjust its scores to match observed frequencies. Isotonic regression can do this flexibly, while preserving the order of stronger and weaker scores. After calibrating each class, normalize the results so the probabilities form a consistent distribution across mutually exclusive classes. Multiclass calibration must be validated carefully because methods such as isotonic regression can overfit when some classes have few examples or the calibration data does not match future cases. Cross-validation and separate calibration data reduce this risk by using predictions from data the model has not already seen. Calibration should be checked for each class and for the full probability distribution, since secondary probabilities can be important in high-stakes decisions, such as clinical triage or loan risk assessment. This script shows how isotonic regression can calibrate multiclass probability estimates. It trains a random forest on the wine dataset, then compares the model's original probabilities with calibrated probabilities using log loss, where lower values mean better estimates. It also plots predicted confidence against observed accuracy, showing that calibration helps the model's confidence better match its real performance. Monotonic probability mapping. Monotonic probability mapping converts a model's raw scores into better calibrated probabilities while preserving their order. This is useful when a model ranks cases correctly but gives probabilities that are too high or too low, such as in risk prediction. Monotonic calibration fixes the probability estimates without changing the ranking, and isotonic regression is a common flexible method for learning this adjustment from data. Monotonic probability mapping helps calibrate model scores when the scores are ordered, but their event rates are uneven. Instead of assuming one smooth correction like a sigmoid method, isotonic regression fits a flexible stepwise adjustment that preserves the score order. This lets it correct different score ranges separately, such as when a model overstates risk at the high end or misjudges moderately suspicious cases, without creating illogical reversals. Monotonic probability mapping needs a balance between flexibility and reliability. Isotonic regression can match calibration data closely, but with sparse or noisy data, it may overfit and learn random variation instead of real probability patterns. Using cross-validation or a separate calibration set helps reduce this risk. When applied carefully, it makes probability outputs easier to interpret and supports better decisions. This script shows how isotonic regression converts raw classifier scores into calibrated probabilities. It fits a non-decreasing mapping from scores to noisy observed rates, so higher scores do not receive lower predicted probabilities. The code checks that the inputs match, learns the calibration curve, verifies that it is monotonic, and plots the original points with the fitted curve. It also reports the Scikit-Learn version and gives the calibrated probability for a raw score of 0.8. In this lecture, you learned to evaluate probabilistic predictions using calibration curves and proper scoring metrics, calibrate classifiers with sigmoid and isotonic methods using cross-validation, and apply isotonic regression for monotonic calibration-style relationships. In the next module, Module 16, we will go over decision trees.
Thank you for your attention. See you all in the next lecture.